I'm grateful for the organizers and for our hosts here in Perimeter for organizing this wonderful, really wonderful event. And I'm too young to tell, but it is my feeling that this is exactly the kind of event that drives a community forward and creates connections between different communities. So again, many thanks. And I had the ultimate pleasure of learning from and working with Yakir Aharonov during the last 5 years. So it was hard to choose on what to talk. Yakir knows that, but Jeff suggested I said something about cosmology. So I'll try. In fact, I'm going pretty much against everything Bill Unruh said, but I'm trying to continue the line begun by yeah, I'm trying. Yeah, that's good.
Sound local right now.
Exactly. But I'll try to continue the lines of the last 2 talks. So the outline is first a short motivation why I'm interested in a final boundary condition in this scenario, and then some preliminaries which you all know. Then, and in fact, I'll combine 2 routes for setting the micro-macro boundary with some special proposals, I mean some special boundary condition to the universe, which implies some collapse mechanism. So this is based, the recent work we had on this is now on arXiv, but this is in fact based on the previous work with Tomer Landsberger, who sits here, and Eyal Gruss, and this in turn is based on the previous work of Aharonov and Gruss. And I say something about Davis. I even use some of Davis' proposals, and also this work of ours. And of course, some new thoughts. Okay, so 4 problems at a glance. Nobody agree these are problems. Maybe these are just features of the theory. But symmetry under time reversal is something which we would be glad to have in a microscopic system. It's rather trivial. In macroscopic system, it might be harder. No time symmetry. Okay. This is why I said, okay, this is one feature, but you'll see it's not really obtained in my suggestion. There is another notion, more general, of time reversibility. So maybe I'm okay. Collapse and the measurement problem, which you all know. Non-locality, again, you'll see in what sense I mean that, and the many particle configuration space. So I believe that two-state vector formalism have much to say about all of these. So first, symmetry under time reversal. Let's imagine some gas concentrated in this half of the box. When we take off the barrier, it would spread in the box, the entropy would rise. This is what we understand as the thermodynamic error of time. Now, Yakir here suggested a very interesting idea that the thermodynamic error of time is really defined in terms of stability under random perturbations. So the forward in time direction is really stable for any small perturbations, but if I make a little change here, it would be very hard to reverse everything. So now I'm making things even harder in the quantum case. Okay, so now basically if there is no perturbation, I can put some final boundary condition, namely reversing all the velocity of all the atoms, and then I will return to the initial state. So this can be easily reversed. But what happens in the quantum regime? In the quantum regime, I can just imagine this gas spreading, but in addition of spreading, I can imagine some atom just collapsing. And now, this is a real problem. If I had a genuine non-unitary evolution in time, how will I be able to restore everything backwards in time, right? This is an actual problem with collapse. Our claim is that when choosing a suitable boundary condition to the system, to the universe, we can restore even this error of time, and still in progress are the cosmological, the radiative, time irreversibility in black holes, where a final boundary condition is, in my opinion, a very, very promising suggestion made on more than 20 years ago by Horowitz and Maldacena and still investigated. So I really think that even in black holes, a spatial boundary condition entangling the infalling matter and the radiation might be able to save reversibility. So again, final boundary condition, I'll try to claim, can help. So the second problem, this was time reversibility. The second problem is collapse. We all know that when the Hamiltonian is Hermitian, we have a unitary evolution in time. This is beautiful, this is symmetric, everything is nice, but this is all true until we have a collapse. And when we have a collapse, this, as we said earlier, inserts a genuine irreversibility, which can be thought as an ugly scar on what could have been a beautiful theory. So this is collapse. Non-locality, I'm just taking some trivial instance. If we have some wave packet and we make a measurement, then suddenly the particle is well localized. Now, how did this happen? And is this consistent with our view of relativity? Well, it is, but in a subtle way, which we discussed here in a Bay-like scenario. So I won't be able to get into this, but non-locality is really a strong motivation for that proposal. And finally, a configuration space, which I, again, find problematic when we are trying to eventually say something about quantum gravity and even just quantum field theory. So this, here again, there were some advances recently, and we are still working on that. So the preliminaries I will run, because this is all the things Yakir taught us during the last few days and last month. So for Neumann measurement, this would be the measurement scheme I would employ. And as you know, this measurement scheme leads immediately to the measurement problem and to the preferred basis problem. So I'd like to understand what makes macroscopic objects macroscopic. Why can't I see a cat in superposition, and why do I see just a single outcome out of the many possible outcomes? So these are all the questions we are facing, and again, in contrary to Bill, I think these are actual problems. But what I'd like to ask instead of all of these is the cat dead or alive? I would reverse it to, is the cat state live or dead? And we would like to claim that in a two-time scenario, the cat is alive. The cat is alive, and you'll see in which way. Many words. Now, Matt Liefer told us that when there is a question in the title, the answer should be no. And I'm inclined to agree, but nevertheless, this is just unitary evolution. So it is a solution to collapse. There is no collapse. I don't need to care about that. I can talk about fuzzy terms in the macroscopic worlds. I can solve this. But as Yakir said, in order to explain what happens in the microscopic world, I need now to discuss many macroscopic worlds entangled with each other with many conceptual and moral difficulties. So I'm looking for an alternative for that. Initial and final conditions, well, I don't need to say much. This is something quantum mechanics allows us. Very differently from classical mechanics, we can talk meaningfully about a final state without having redundancy and without having some contradiction with initial conditions. So this is really special in quantum mechanics. And this has led to many results. I usually go through them, I won't. But we all know that this has been tremendously useful in many cases. ABL rule, okay, I don't need to say much about that. And of course, the two-state vector formalism, which I'll use. So even in a cosmological scenario, I would like to assume some initial quantum state of the universe propagating forward in time in a unitary, in just unitary evolution. And in addition to it, I would like to add some final state. Now, a final state as well as an initial state are big questions in cosmology. What could be the right state? So I'll show you, I'll try to bypass the hard questions and just talk about the simplest meaningful case I'm able to. But this again is our scenario. So we have initial condition going backwards in time, we have final condition, I'm not sure who put it, I'm not sure how it arises. I'd like to, but I don't know. What I do know is what to do with it. And I'll show you what we can do with a final boundary condition put now on the universe. And the meaningful object, the important thing to discuss now is not the state vector, it's the two-state. So the two-state now gives rise to something else, to a two-time density matrix. We don't discuss anymore density matrices. We are not concerned now with many problems of entropy of density matrices because we now have something completely different. It's a two-time density matrix. And Yakir asked, how can we feel these future effects? And we now know the beautiful answer. We can sense final boundary conditions using weak measurements. So we just replace the von Neumann coupling with a very weak one. We can talk now about several things. The first thing I'd like to mention is that, as Alonso said, weak measurements are really ubiquitous. And in fact, the state of a large ensemble was shown to be nearly an eigenset of any average operator. So you just prepare a large ensemble, and this operator would have it as an eigenstate. Now, why is this important? This is important because in the real world, when I want to just measure the position of this pointer, I can really simulate it by measuring all the positions of all atoms and an average. But what is this interaction Hamiltonian? This is a weak interaction Hamiltonian with respect to any degree of freedom. So all our measurements in the macroscopic world are essentially weak measurements of the smallest degrees of particle. We have a natural weak interaction here, which is 1 over n, when n is the size of the object, and n is the total number of atoms in the object. So all our macroscopic intuition we can state it in terms of weak measurements of single degrees of freedom, and moreover, what we find is a set of operators commuting. So as Lev said, everything is really quantum, but in cosmology we can just sometimes, or in the macroscopic world, we can forget about these quantum features and talk about commuting deterministic operators. So this is what I'd like to do, and what I'm suggesting, also Davis said it, all our macroscopic and in fact all our cosmological observations are naturally weak, but this is in fact trivial, because when I see photons coming at me from light years, I have practically no back action on those systems, right? So I can see the photons, I can learn something without disrupting what I see. This is pretty trivial, but I find it interesting because it allows me to discuss the macroscopic world just with the quantum two-state vector. And the nice thing, as we know it in all our analysis in the works of Jordan and Dressel, and the square root of n would always come to rescue us. So when we are talking about macroscopic objects, there is a good reason they should be macroscopic. We can avoid in this way the quantum uncertainty and talk meaningfully about those systems. Without having macroscopic objects, we could not have been able to say something meaningful about the world. and especially about the universe. So cosmological boundary conditions, as I said, this is really hard. What I'm trying to say is we now understand that the universe was characterized by a period of inflation. So at least it's...
Sorry, I can't believe it there. I thought this conference is about critical thinking.
Okay. This is... I see. So...
Maybe I'm in the wrong context.
No. You are exactly. You are exactly. This is just a proof of principle. This is a proof of principle. I'm saying, okay, I'm putting it differently. Let's assume, just hypothetically, I'm choosing out of all possible space-times, I'm choosing for some reason the de Sitter space, and in the de Sitter space, the good thing, why I'm choosing it, because we can just take one state, for example, the Bunch-Davis suggestion, and say, okay, this is our initial state, and we can go on from now. And okay, again, if we assume that the universe is dominated by dark energy, we can assume a final boundary condition, which is again de Sitter invariant. So this is good, but we need to add something more. And the two-state vector formalism allows us to choose different states as long as they are not orthogonal. So I can really choose, and this is the point, not that specific example. We can really choose those initial and final conditions which obey some symmetry, and we can make them non-orthogonal, and we can even, to be more interesting, we can say that they cannot be related by any unitary transformation. And this allows, for example, again, to use suggestions like the width for reformulating the Einstein equation. So I'm replacing, he replaced the energy momentum tensor with its weak value, essentially. So I'm not sure what this says about G mu nu, but this is a weak value, and this is what Yakir is talking about.
Sorry, why can they not be related by a unitary transformation?
No, they can, but in order to explain collapse, I would need them to be somewhat distinct. So I'm
sorry,
this is a
here. What was the distinction here between collapse?
You'll see in a few slides. I want to use this freedom I have from the two-state vector formalism. In the two-state vector formalism, we are making a projective measurement at the end, right? We are making post-selection. Now, I can't discuss post-selection in the universe, but I would like to discuss some interesting final boundary condition, not just the unitary evolution of the initial state.
So you don't mean that the two states are in different Hilbert spaces, because this
no,
happens many times.
Right. I can't say such thing with respect to the universe.
Same Hilbert space.
Yes. Okay. Why I find this interesting? There are two instances where I find this especially interesting. I again would not be able to talk much about this, but as I told Lucian earlier. The pigeonhole scenario, for example, these are again just examples, just to see the potential of this method. So the pigeonhole scenario enables to break monogamy of entanglement, and if it allows to break monogamy of entanglement, it allows us to say something about the firewall. It allows us to overcome maybe some of the difficulties. Another interesting idea, now a recent idea of Yakir, is the atom of Holism, which suggests a completely top-down logical structure of reality. And this is again very nice, and this again suggests that correlations are eliminated, the lower order correlations are eliminated until we reach a highly non-local state. And this again resembles something I think about what we think about quantum cosmology. So, after talking very generally, I would start, as Yakir always says, with the simplest example of these ideas. So let's assume our system is composed of some superposition of a two-level system with a pointer in the ready state and some environment state. Now I perform a von Neumann interaction and couple this pointer with the measured system. Now, after some decoherence time, which we see in the lab, this is just an observational fact, these would be separated. This would be now entangled states corresponding to two environmental states, epsilon1 and epsilon2. Now, epsilon1 and epsilon2 are almost orthogonal, and now I want to understand why everybody says that I can't see those in reality, right? I cannot see two macroscopic states which are orthogonal. So why is this the case? This is the case only if we can assume a backwards evolving final state. Okay, so we had our initial preparation, it went forward in time, and now we have a final state. Now, answering Ephraim, here is a special boundary condition. It corresponds to one of the environmental states. It can be somewhat different from that. This is again an example. We have much more freedom than I used here. But I can just assume a final boundary condition which corresponds to one of the environmental states. If this is the case, I can now use the two-state-vector formalism to discuss reality in a new way. My ontology now is not the one state, it is the two state. And as Lev told us, when we examine the initial and final boundary condition, we need to look for an overlap between them. So now I see a clear overlap between the environmental state epsilon1 in initial and final conditions. So I can meaningfully discuss the reduced two-time density matrix corresponding to this pre and post selection. And this effectively leads to collapse, because in effect this is what I'm working with. I have just a reduced density matrix, and this density matrix now suggests that my measurement device was really in the first state and my microscopic state was the corresponding one. So reality is effectively described by a single outcome within the two-state-vector formalism. So this was too simple, maybe. So we can generalize it, and in fact we did. We can encode now many sequential measurements, maybe even a very large number of sequential measurements in the final state. We can also discuss continuous pointers, not necessarily discrete. We can discuss mixed state, and we can add in some interesting intermediate dynamics. So these are pretty straightforward, except for the first, which demanded some work. Now, I think that the most interesting generalization would be to assume that also macroscopic objects collapse. And this generalization, which I find again very natural because everything is quantum, so everything can collapse in some stage. So now I would like to discuss this case where not only microscopic objects collapse, but also macroscopic objects. And then the question is a hard one. If my record of the microscopic world is now decaying with the macroscopic world, will I be able to rescue it using a final boundary condition? This is not a trivial question, I think. And the restoration now demands something interesting about the macroscopic world. It demands that the macroscopic world would be rich enough to contain all the microscopic information. And again, I'm saying again because we now understand error correction codes as very, very close, conceptually close to ADS-CFT. So error correction, I assume, is important also when trying to understand the interplay between micro and macro worlds. So I'm again asking the question, what will happen when the environment collapses? So I need now to assume two trivial things. First, that collapse never leads to an orthogonal state. Now, this is well known, but this would play a major role in the next slide. The other assumption, which I'm still trying to convince Lev about, is it is impossible to measure an Avogadro number of degrees of freedom. Okay, I don't believe we would be able. I don't think this is what makes. This is why we can't falsify the many worlds interpretation, because we cannot store in one place the information about an Avogadro number of quantum particles. Okay, so those are the assumptions, and this is my only technical slide. I start from the same entangled state after the decoherence time, but now I assume that the environmental states decay with time. So I had n degrees of freedom, out of which smaller n collapsed and capital N minus small n remained. My assumptions about orthogonality are here, so I never collapse into an orthogonal state. And I'm choosing some special boundary condition again, which just overlaps my state after decoherence. Now this would restore again just one macroscopic result, and this, more importantly, will allow us to discuss something we call the robustness ratio. The robustness ratio tells us what is, it gives us indication about how successful was the time reversal. So if the time reversal was successful, if I'd like to believe that there is zero probability for the time reversal to fail. So in this case, this puts the limit between micro and macro worlds. I need to tune this inner product between environmental states so that this thing would be larger than 1. So if I really want macroscopic objects to hold all information until the final state of the universe arrives, I need to assume a special size. They must have a special large size in order to facilitate all the information. So I know I need to finish, so I'll go to my bottom line. This is, okay, my bottom line. My bottom line is that Yakir has effectively shown us a subtle local hidden variable theory. It is subtle because the particles, as Yakir put it, didn't know what would be all possible measurements. They knew exactly what would be the measurement I would do, and this, as Unruh said, this is non-locality in time replacing non-locality in space. But I personally love this idea, and this leads to a built-in collapse mechanism and a natural micro-macro transition. Okay, so thank you very much.
Time for a few questions. Ivan.
So, I admit I was not able to follow all the details, but is it are you presenting a descriptive tool, or do you have some predictions to make?
I think both. The prediction would be, we need, okay, I skipped this slide. We have 3 important factors. One which I would like to determine experimentally, what makes a macroscopic object macroscopic. The others are related to how many collapses are possible within the lifetime of the universe. So this is not a simple question, but if we are able to set this number, we can set the micro-macro boundary.
Okay. So I realize you construct state, but still I don't know the relevance of that state in the actual de Sitter state.
Yes, so we have unitary evolution, right? So I can assume that at some point there...
But de Sitter vacuum has its own meaning. I don't see that this is a de Sitter vacuum here.
Right, because it evolved unitarily in time. But the nice thing about unitary evolution is you can just plug it into the weak value formula, to the ABL formula. It fits nicely. So this is always an ingredient in the theory. You don't really need to care about this. Okay? And this was basically the claim.
Okay, Jason Thomas, just want to comment. I call him little Thomas because we have two Thomas. So there is big Thomas, which was mentioned here, and here's little Thomas.
I just think that the paper of collapse within the two-state-vector formalism is very, I think that it shows us that the TSVF is like a domino, that from this theory we can understand a lot of quantum phenomena that cannot be understood within other formalisms, like the many more still.
Yes.
I just don't want to go there, but
Yes.
this is
You have to wait for him. Oh,
Yeah, of course I agree. Yes, thanks.
Okay, so let's thank our speaker again.